Hello everyone, welcome to this video tutorial on analysis of the step bar in Ansys Workbench and SpaceClaim. So the contents of this video is like this. Hello everyone, welcome to this video tutorial on analysis of the step bar in Ansys Workbench and SpaceClaim. The contents of this video are like this. We'll be starting with the learning outcomes, then problem definition, then material modeling or material properties, then geometrical modeling, then meshing of the geometry, then applying the boundary condition and forces and analyzing the results. And at the end of the video, there is an amazing challenging problem based on this learnings for you. So the learning outcome of this video, after this video lecture, you will be able to model the bar elements in Ansys Workbench using SpaceClaim. Then you will be able to apply various forces and boundary conditions on the bar elements, and you will be able to calculate deformation and axial forces and the reactions at fixed nodes or boundary conditions in bar elements. So let's move to the problem. This is the problem we are going to solve. Now we have to determine the nodal displacement, axial forces and reactions in the following axially loaded step bar. So the problem is like that. We have three elements, element 1, element 2 and element 3. I'll do this thing, arrow option we want, okay, let it be, yeah, here we have laser pointer. Okay, so this is element 1, this is the element 2 and this is element 3. Now the properties for element 1 and 2 are same, and properties for element 3 are different from element 1 and element 2. There is a nodal force at node 2 in positive x direction, 3000 newtons. Each element is of 10 centimeters, and we have node 1 and node 4 of fixed displacement, that is displacement at this node 1 and node 4 is 0. Okay, so let's move to the material properties. Two different materials are given. For element 1 and 2 we have the same elemental properties, and element 3 we have different elemental properties. Okay, now we need to add these materials into the Ansys. So the property E is given, we have to assume the Poisson's ratio, and here we are going to assume it 0.3, that is standard one. Okay, so let's go to the Ansys and create a problem or analysis system. So we are going to solve this problem using static structural, and we have to model the materials. So you have to double click on this, and you can see here, click here to add a new material. So click here and give a name material real 1. So this will be the material 1. Now you have to add the properties to this material. So we need isotropic elasticity to this material. Double click on this isotropic elasticity, and you can see here this isotropic elasticity will appear here. Now here you have to fill out the properties. So temperature you need not to fill it. Now Young's modulus, we'll go to the slides. So Young's modulus is 10 into 10 raised to power 10 pascals. So the units here are in pascals, so we'll directly write 10 e to the power 10 pascals, and the Poisson's ratio you have to assume it's 0.3. okay, so that's it for material 1. We have given the material properties for material 1. Okay, now we will add the material 2 as well. So this is the material 2. Now also add isotropic elasticity to this material, then again slide this somewhat, and now what are the properties for material 2? Material 2 we have 5 into 10 raised to power 10 pascals. So we'll go to the Ansys. This is 5 e 10 raised to power 10 pascals, and the Poisson's ratio is 0.3. So let's check once again. Yeah, 5 into 10 raised to power 10 pascals. Okay, so that's it. You have this materials in your library. Now you need to suppress this structural steel. To suppress, you can click on this checkbox and you have this material 1 and material 2 ready for the analysis. Now you can close this engineering data I'll say tab, and your data is ready. Now let's move to the slides once again. Now we have finished material modeling for these two isotropic materials. Okay, now let's go to the geometrical modeling. We have two different areas, like area 1, that is 1 centimeter square. The corresponding radius will be root 1 by pi, that is equal to 0.5642 centimeters, and we have area 2, that is 2 centimeters square, and the corresponding radius R2 will become 0.7979 centimeter. Make sure that or remember that we are considering circular rod as a cross section area of or circular rod as a member, and the cross section area then it will become a circular, so we have to calculate the radiuses. Okay, then we'll go to the geometry modeling. We click right click on geometry and we'll open a new SpaceClaim geometry. So it's starting new SpaceClaim window. So it will take some time. In meanwhile, we'll see what we have to model. So we have to model a bar element using this dimensions 10 centimeter, 10 centimeter, 10 centimeter. So we have three elements of 10, 10, 10 centimeters, and we have to assign them a cross section area, a circular cross section area. Area 1 is 1 centimeter square and area 2 is 2 centimeter squares. It's taking some time. Okay, we'll see the next slide as well. So after modeling the geometry, we'll again come to the workbench and we'll open the mechanical Ansys mechanical modeling GUI. In there we will be meshing the elements. Here also we have to consider one element per member as a meshing size, and the type of elements will be beam 188, and these are the types of element available for 1D analysis of step bars or bars, I will say. Then these elements have 6 degree of freedom at each nodes. Then we will apply this boundary condition. We have fixed support at node 1 and node 4. Then we will apply these forces. The forces we have like 3000 newtons in positive x direction at node 2. Then we'll analyze these results. Total deformation at node 2 and node 3. Then axial forces in each members and reaction forces at node 1 and node 4. So these are the results for nodal displacement. At node 2 we will get a displacement of 0.002 centimeter, and node 3 will get 0.001 centimeters. So these results I have calculated manually, and these are the axial forces. For element 1 we'll be getting 2000 Newton in tension. For element 2 and element 3, those two elements will be in the compression with minus 1000 Newton force. And these are the reaction forces. At the node 1 we have minus 2000 Newton, and at node 4 we have minus 1000 Newton force. So now our static structural SpaceClaim GUI is open. Very first thing, you have to click on this layout sketch. You must click on this thing and you have to set the units. So we'll go to this file menu, then file, from file menu this will appear units, then millimeters. You have to change it to the centimeters and click on OK. So this is here, file, SpaceClaim options. Okay, now you have to select the plane. We have to select this XY plane. To change the plane, you click on this thing, select new sketch plane, and you can toggle between the planes like this. So you have to select this XY plane, click on this plane, and you have to see a top view of this plane. So to switch to top view, you have to click on this plan view. So this plane orients to the screen plane. Now you can start modeling the bars. Take a line, start with this 0 and give 10 centimeter line, click OK. So this is a 10 centimeter line. Again we have to model the element number 2, that is again a 10 centimeter, and next element is also 10 centimeter. So we have 3 elements of 10 10 10 centimeters. You can see here, this is 10 centimeter, this is 10 centimeter, this is 10 centimeter, and this is also 10 centimeter. So we have element 1, element 2 and element 3 structure ready. Now you have to click on this end sketch editing. Okay, so you have done with the sketching. That's it. You can see here we have 3 lines, line 1, line 2 and line 3. Okay, so this is this is okay, fine. Now you'll have to switch to this prepare thing, prepare module, and we'll go to the profiles. Now we'll create the profiles as we have decided to go with the circular profiles. I'll select this circle 1. Okay, now this will appear here as a beam profile. Okay, so beam profile here, you just change this to the area 1, area 1. Okay, again we'll add one more circle here and we'll change this name to area 2. Okay, so we just have renamed these things. Okay, now right click on area 1, go to edit beam profile. Okay, so once you go to edit beam profile, you can see here this is radius 1 centimeter, and you can see here ruler dimensions. You have to click on this ruler dimension and click on this 1 centimeter. So in 1 centimeter you have to apply the radius 1 dimensions. So you have to apply this r1 is equal to 0.5642 centimeters. So we are here 0.5642 centimeters and enter. Now you can see here 0.56 centimeter is open. Now we have changed the area. Then you have to go to this design and click on structure again. Then you can see here area 1 is done. Area 2 we have to do the same thing, edit ruler dimension 1 centimeter, you have to change it to this 0.7979 centimeters, then 0.7979 will work. So this will become r is equal to 0.8 centimeters. Okay, now then you have to close this SYS1, SYS2, and this is the remaining thing. Then the structures. So your area 1 and area 2 profiles are ready. Then you just have to apply these profiles to these lines. Now in line 1 you have to apply area 1. So you have to click line 1 and line 2. So these are the two, line 1 and line 2, and you just have to click this area 1 here. So you have applied a beam profile to this first two lines. Then in line 3 you have to select area 2. Now if you want to see that you have applied correct areas, you can check this display, change this display method to solid beams. Now you can see here we have these two elements with the area of 1 centimeter square and this third element with the area 2 centimeter square. So after doing this thing, you just have to go and select all these beams, right click on all these beams and click on move to new component. This is very important, uh, making this all components as a one components, because we have to share the forces among all the elements, and that if you do not do this step, you will miss or you will not be able to formulate the problem correctly. This will not work, this will give some errors. So you must click here move to new components. So now you can see here, you have beam. Okay, you have beam area 1, area 2 and area 3. Now you have prepared the areas, then just go to this workbench, prepare and workbench and click on share topology. Click on share topology. You'll see here found two vertices. Click on this OK. Okay, so you will see like this. There is in one orange, green and orange element. So that's it. You have completed the geometrical modeling for bar elements. Okay, then we'll go to this thing. Yeah, done. So you can close it or you can minimize it. Okay, now we'll go to the workbench again. So we have done the modeling of materials, we have done the modeling of geometry, then we will go to the Ansys mechanical for further processing. So it will take some time to open the Ansys mechanical. Yeah, in the meanwhile we will revise the remaining things. So we have done with the material properties and geometrical modeling. We have modeled these two areas, cross section profiles with a circular rod. Then next thing is we have to do a meshing. Okay, so let's see what is it ready. No, it's starting. So we have to do meshing. First of all, we'll check everything has been imported in this Ansys mechanical model. Yeah, it's opening now. Yeah, it will take some time, few more minutes. You can see a progress here. Yeah. Okay, so you have this geometry here. You can see the geometry. Okay, yeah, that's it. You can see the geometry. Geometry is imported. What's the problem with the components? The components we don't have added the material property. So this beam area 1, we have to apply the material 1. So material property, just assignment, material assignment is pending and you just have to add the material 1. Okay, so we have added the material 1 to beam 1, then you have to add the material to beam 2 as well. That's done. So we have added material to beam 1 and beam 2. You can see here material 1 and material 2 is ready in your project form folders. Then cross section area 1 and area is also there. Then coordinate systems, we have all the coordinates, global coordinate system connections you need not to define. Now you will go to mesh and insert sizing. In the sizing option you have to select the geometry, so you can use the scooping method, walk select, and we want all the nodes, so all the elements. Okay, yeah, edges. So apply and apply. Now you have to change the method. You have to change the method from type element size to number of divisions, and you have to make number of divisions to 1. So you can see here we have 3 elements. That's perfect thing. Then you just right click on the mesh and click on generate mesh. Okay, now if you want to see these things, you go to display and thick shell beams. So you have this thing. Okay, so these are the element, this is the element 1, this is the element 2, and this is element 3. Now we'll go to the static structural and right click and insert. So we have to fix the 2 nodes. So this node will be fixed and this node will be fixed. So you have to apply a single select option and apply this thing. Geometry, you have to select this node, apply, and we have fixed support here. Then again you have to go to the static structural, insert, and fix support. Then click on this edge or this node, and this is, so we have given the boundary conditions. Then apply loading. So insert force and click on this node number 2, apply. Then instead of vector you have to do component wise components. Then in X component we have 3000 Newton force. Okay, that's it. So if you have to see all the boundary conditions, all the applied boundary conditions and the forces all along with, so you can just click on this static structural. So this is the fixed node, this is the fixed node, and this is the applied force 3000 Newton. We'll just cross check it with the geometry. So this node and this node is fixed and there is 3000 Newton force applied in positive X direction. So that's it. Okay, now what we will do, we will add the results. What results we want? We'll add a total deformation, then we'll add probes. So we want a deformation geometry selection. Yes, we'll select this geometry, apply, and what we want result in x-axis, along the x-axis. Then again we'll go probe deformation, we want a deformation here, then apply, then result selection, you have to apply x-axis. Okay, then we have applied the nodal displacements. Then go to the probe to add the force reactions. Then you have to select this force reaction 1. Again we'll go to probe force reaction and at node 2, sorry, force reaction support 2. Okay, then last thing, you have to go to the beam results and axial forces. So that's it. You have added all the required results. Just right click and sort. It will give some warnings, but that's fine. And if it is going to solve this thing, so it is solving the mathematical model, and yeah, the results are ready. So first of all, what results are required to us, we'll go to the slide and we'll check the total deformation at node 2 and node 3. Okay, so the values are 0.02 centimeters and 0.01 centimeters. Okay, so this is the total deformation. Okay, the total deformation in meters. If you want to see it in centimeters, you just click on this thing and centimeters. So these are the values in centimeters. So here we are getting 0.02 centimeters, and here we are getting something, let's say near about 0.01. So if you want to check the exact values, we have added the probe. So this deformation probe shows this value. in the centimeters. So 2 into 10 raised to power minus 3 centimeters, that is 0.002 centimeters at here. Then we have this thing, this is 1 into 10 raised to power minus 3 centimeters, that is 0.001 centimeters. So if you add this thing and this thing, is it possible to see? No. So this is how you can see the results. If you want to see the animation, you can click on this thing. So this is how you can see the animation as well. Now what we will do, we will just copy these results, probe data, and this probe data results image to clipboard, and I'll paste it here. Okay, so no, it's not possible. You just have to go you have to paste it here, results. So this is the deformation probe 2, and you have to copy the table as well. So export or copy cell, if it is possible, copy and paste it here. So this, I don't think so it is getting the correct values. You have to export the values, export, and you have to save it somewhere. So I'm saving it FM. We have analysis of step and deformation at node 3. Okay, so this is deformation at node 3. Then okay, so again we'll go to this is open. You just copy this thing. Now you can see the number or keep it general format. Okay, Control C and let it be open, Control V. So we have this values here. Okay, for the displacement pro 1, sorry, at node 3. Similarly, we'll go to where static structural, just click on node probe, copy image to the clipboard and go here, paste it here. Sorry, now you cannot go here, you have to go here and you have to paste it here. So this is element or node. Okay, this is node 2. Go to this thing and just click on export, then again and deformation at node 3 and node 2. Okay, so you have exported the values. Then you can also click the image or take the image of this thing and just paste it here. Yeah, so this is the total deformation. This is deformation at node 2 and node 3. Then we'll go to the axial forces. These are the axial forces. Again, these are in centimeter dyne, so we want this forces in newtons. So Newton we have 2000 and minus 1000. So this is the bar element 1, which is in tension, and the force is 2000 newtons. here we have the forces minus 1000 newtons. So we'll take this image, copy it to clipboard, and Alt to paste it in place of this axial forces. So you can see here these are the forces. Again, if you want, you can also export these results as well. So export, this is axial then let it complete. Then this is the force reaction at node 1. Now what we'll do, I'll just reduce the size of this, so we'll get so if we copy this image now, this will be of the same size. So so that's the result, and we also export the results for this thing. Export. Sorry. So the step bar, I will save the results. Reaction force at node 1. Is that correct? Yes, reaction force at node 1. And we'll do with the same thing with this force reaction 2. We'll paste it here. Now we'll just wait. We have the reaction force. We'll just export this PC FM step bar and reaction force at node 4. That's it. Then we'll go to the axial force. This is the minimum and maximum values in newtons. Okay, we'll copy this thing. We'll go to the slides, and where we have to paste it, here. These are the results. Okay, then we want this as well. So reaction forces at, this is at node 4. Okay, let's do this like this. So we want this value only, 1000 newtons. These are the negligible forces. You can see here. So total is 1000. Now we'll copy all these things. Okay, no issues, and we'll paste it here. Some error. Copy and paste. It's working. Now you just have to change the color to white. Then we'll go to the reaction forces at node 1. Control C and Control V. We'll just change the color to white. So that's it. The results are ready. Then we'll go to our slides and we'll check the results. Okay, so we want nodal displacement at node 2 and node 3. We have u2 is equal to 0.002 centimeters. So we got this value. We have not pasted. So deformation at node 2, deformation at node 3. So this is node 2. We want this value to be number and then general, so it will become 0.002 centimeters. So we'll go and paste it to this thing. Then we'll check it in slides. Okay, so we have this thing. node 2 the displacement is 0.002 centimeters, and node 3 it is 0.001 centimeters, and this is the total deformation plot. Then we have results for axial forces. Element 1 that is 2000 Newton. You can see here a red color 2000 newtons, and minimum -1000 newtons for element 2 and element 3. Then these are the reaction forces, the force reaction at node 1. So this was the node 1, and we have the value of 2000 newtons in this direction, that is -2000 newton, and we have at the node 4 -1000 newtons. So we have validated the results as well. Then this is a challenge for you. You have this configuration of the step bars where we have this elements 1 2 3. This is the node 1 2 3 4. We have 50 kilonewton force here at node 2 and 50 kilonewton force here at node 4. This is 0.5 meter, this is 0.5 meter, and this is 0.5 meter. This diameter directly is given here, 0.1 meter, 0.075 meter, and 0.05 meter. Then elemental properties are given for element 1 and 3. Element 1 and 3, 70 GPa, and for element 2, that is 180 GPa, and P we have to use 50 kilonewtons. Okay, so you can solve this problem for total deformation at node 3, node 4, node 2, 3, 4, axial forces and reaction force at node 1. So all the best for this challenge, and thank you for watching this video. Please like, share and subscribe to this channel. Thank you.